Let's discuss about velocity and acceleration of a particle in SHM. For SHM, as we already studied, in general, displacement of a particle in SHM is given as y is equals to a sine of omega t plus alpha. And if this is the displacement as a function of time, velocity of particle can directly be calculated as dy by dt, which is giving us a omega cos of omega t plus alpha. We have just differentiated the expression with respect to time. And these are expression 1, which is giving us velocity as a function of time during SHM of a particle. We can also transform it into velocity as a function of displacement, as we can write it. A omega cos of omega t plus alpha can be written as 1 minus sine square omega t plus alpha. And here if it is sine square omega t plus alpha, it can be substituted from here, which is y by a. So here velocity can be given as a omega root of 1 minus y by a square. On simplifying, we'll get omega root of a square minus y square. There's another important term we need to keep in mind. This first as well as second, both of these expressions are quite useful, which are giving us idea about velocity as a function of time and velocity as a function of displacement. From here we can see at mean position of particle y is equal to 0. This implies if we calculate the velocity, this maximum, its value is a omega. And obviously at extreme position, as y is equals to plus minus of a, the minimum velocity of particle, if we get from this expression, it is coming out to be 0, which we know at extreme position velocity is 0, and at mean position the particle moves at the maximum speed, that is a omega, in either direction. So just keep both of these expressions in your mind. Whenever in analytics you need to use the time function of SHM particle velocity, you will use expression 1. And whenever you need to use displacement function of SHM particle velocity, we will use expression 2. As we have just discussed that velocity of particle in SHM is given as a omega cos of omega t plus alpha. We can calculate the acceleration of particle simply by differentiating in the term of velocity as dv by dt. So this will give us, if we differentiate the term, it will give us minus a omega square sine of omega t plus alpha. Now in this situation, this a sine of omega t plus alpha can be calculated from our general equation of SHM, which gives us y. So it will be minus omega square y. If you substitute y as a sine of omega t plus alpha, we are getting acceleration. So these two expressions are giving us the acceleration as a function of time and acceleration as a function of displacement. So just keep both of these expressions with you, because these are quite useful in analysis of acceleration of particle in SHM. From here we can also calculate that at mean position y is equal to 0. This implies if we calculate the acceleration at mean position, acceleration is minimum, which is 0. And at extreme position, y is plus minus of a. On substituting this, the magnitude of maximum acceleration we are getting is omega square a. So just keep it in mind. And I've taken magnitude, otherwise sine is only giving us, always it is acting toward mean position of particle. Sine is just giving us the idea about it. Now from equation 2, if we just rewrite it as d square y by dt square is equals to minus omega square y, then it can be rearrange that d square y by dt square plus omega square y is equal to 0. Now there's another expression which is quite useful, and this is called basic differential equation of SHM. Whenever a particle executes SHM, whenever it executes SHM, its displacement as a function of time follows this expression which is called basic differential equation of SHM.